Hi everybody, it is Mr. Cat here. Hope you are doing well. So I'm going to walk you through some of these problems and some notes on inverse functions, and then it'll be up to you to do any problems that are not done on these videos. Okay. Let's start with something that you have done before. Try graphing these inverses. So go ahead and pause the video now. Try to graph these inverses, and then I'll show you my answers. So go ahead. All right, so hopefully you're able to do that. Let's double check. So what I am going to do is start with some nice points here and invert them. So this is negative 5, 0. This is 5, 10. I'm going to go ahead and graph those. Now, one thing that's important here is that they're open circles, right? So that's 10, 5. And negative 5, 0 becomes 0, negative 5. Those are sort of anchor points here. Negative 5, 0, oops, sorry, 0, negative 5. Right. Now another point that I see here is that is 0, 5. So I'm going to plot 5, 0. And you do want to make sure you get the correct shape to this. So you might want to find another point like this is, looks like negative 1, 1. So I want 1, negative 1 there, and now I start to see the shape start to form. Another point you might want to try is 1, 9, and that goes to 9, 1. And now I definitely have this shape, and I can see it's a reflection over that diagonal line y equals x. Right? Tilt your head a little bit if you have to, just to make sure it is symmetrical. Now, one thing we talked about last time is this buy one, get one free, right? So our domain of f of x, hopefully we see is negative 5 to 5. I'm not including the points, the endpoints, because there are open circles there. And right off the bat, right, I know my range of my inverse should be the same, negative 5 to 5, right? Okay, so now I look at the range of the red function, the original, 0 to 10, right? And I know, oh, okay, wait a second. That's buy one, get one free over here. 0 to 10 is the inverse there, right? And I can scan across. That makes sense. 0 to 10 for my inverse. And negative 5 to 5 for the range of my inverse. Hopefully that one checks out, okay? Now, both of these are functions, right? We can take, now that we've graphed both of them, we can look at the vertical line test for both of them. However, as we figured out last class, that is not always the case. So this one, right? Some of you may recognize this as a trig function, right? And it's okay if you don't, right? It's either a sine or cosine curve. But let's check this out. So the domain, let's start with the domain of this. Looks like this is going on forever. We're going to assume this is going on forever. Okay? In the x direction, right? So all of these values from negative infinity to positive infinity in the x direction have a value on this graph. Let's see if we can do the inverse, though. It seems as if we have this line down the middle, right? And that might be a good place to start to graph, right? So I can see, for example, that the point 0, negative 5 goes to negative 5, 0, right? If I start to graph all of these points down the middle, I start to realize, okay, this is, what, 2, negative 5. That's going to go to negative 5, 2, right? All of these points are on the inverse, and we start to realize, wait a second, definitely not a function. Okay. Might help to get a couple other points here just to make sure we can graph this correctly, right? We get negative 1, negative 3 becomes negative 3, negative 1, right? And then we start to see that the shape starts to form. Okay, this point here is 1, -7. So we'll do -7, comma 1. And now that kind of gives us the shape. So here is our inverse function. I shouldn't say inverse function, I should say our inverse relation, because this is certainly not a function, right? To go back to domain and range, the range of f of x, well, it stays within this whole time, right? So it stays within -7, right? This is -7 to -3 the whole time, right? It never leaves that space, right? And as we've talked about before, -7 to -3 becomes the domain of the inverse, right? And the range this time, the range goes all the way up to infinity and down to -infinity, right? Which matches the domain of the inverse, of f of x, I'm sorry. But we've seen before, the blue function is most certainly, or the blue relation is most certainly not a function, right? The original is, but we've talked about it before, it does not pass the horizontal line test, so the inverse will not pass the vertical line test, right? We will define that as a special type of function, this original red function, in a bit. But let's talk about some algebraic and numerical sort of mini investigation on what truly makes two functions inverses of one another. So right here we see f of x and g of x, right? They have different rules, but let's see what happens when we make a quick table of these, right? So if I plug in 1 here, right, f of 1, hopefully we see, right, we get 2, right? And, you know, we could keep going, right? F of 3, 3 plus 3 is 6 over 2, gives us 3. F of 5, 5 plus 3 over 2 gets 4. 7 plus 3 over 2 gives us 5. 9 plus 3 over 2 is 6. Now, obviously, these are not the only points that I can plug in, right? I can plug in anything, right? I designed this to get some nice points out of it, right? Odd numbers plus 3 over 2 will give us some nice even numbers, right? So let's not mistake the fact that we can plug in anything we want into this function. There's no restrictions on it. Now, let's check out 2x minus 3. If we plug in 2, right, g of 2, we get 2 times 2 minus 3. 4 minus 3 is 1. Okay. 2 times 3 is 6. Minus 3 is 3. G of 4 is 5. G of 5 is 7, right? 2 times 5 is 10, minus 3 is 7. G of 6 is 12, minus 3 is 9. All right, so we just filled in a quick table of values. Obviously, those are not the only values either that we could plug in for G. But hopefully we notice something from these tables. So take a look. What do you notice? Hopefully you're seeing, right, that the point 1, 2 is on f of x and the point 2, 1 is on g of x. And that happens all the way down for these values, right? So we're noticing that the x and y values are switched, right? X and f of x. So based on what we know, maybe these are inverses, right? The reason I say maybe is because we can't just look at 5 points and notice that they switch the x's and the y's switch, or the x and the f of x or x and g of x values switch, right? And I should say the inputs and outputs switch. We don't know just based on these points, right? It's not enough to just look at well, 4 or 5 points, right? Well, let's see what happens if we start to compose these functions with one another. So let's do f of g of 10, right? Well, g of 10, if I plug that in, right? G of 10, 2 times 10 minus 3 is 17, right? Now, f of 17 is 17 plus 3 is 20 over 2. I get 10. Okay. Well, what if I did g of f of 21? Well, 21 plus 3 is 24 over 2 is 12. G of 12, 2 times 12, 24, minus 3 is 21. Okay? Go ahead, pause the video now and do f of g of 0 and f of g of negative 5. Okay, hopefully you got f of negative 3 and you got 0, and then hopefully you got f of negative 13 and you got negative 5. And what do you notice? Well, look at this. The original input into all of these compositions, in other words, the number that we're plugging into the inner function of all of these turns out to be the input at the end, the output at the end of the composition. So you plug in 10 as your original, what you'll get out is 10. Plug in 21 as the original, you get out 21 at the end. Notice how we also had some of these that were f of g of a number and some were g of f of a number, right? So the original input is always the output. Okay? So what we've done so far is just explore these. We haven't really concluded. We have a strong feeling that they are inverses, but we're about to do the most powerful thing that we can do to actually prove that these are inverses, okay? Let's take f of g of x and g of f of x. So we know from our rules, f of x is x plus 3 over 2, g of x is 2x minus 3. So let's do f of g of x first. That's going to be, right, we substitute in the entire expression of g of x inside of f of x, that's 2x minus 3. And we look up there, our rule is x plus 3 over 2. So we're going to take that, 2x minus 3 plus 3 over 2. Okay. Right, that was our input. Hopefully we see, okay, wow, look, negative 3 plus 3, that's 2x divided by 2. Wow, that's just x. Interesting. Let's try g of f of x. All right. So that this time we're going to take g, and inside of g we're going to take f of x, which is x plus 3 over 2. And we're going to apply g of x to that inner function there. X plus 3 over 2. We got minus 3. Look what happens with the 2 and the 2 there, right? You have 2 times x plus 3 over 2, but we can really say that those 2's cancel, right? And you're left with x plus 3 minus 3. Wow, that equals x as well. Look what we got. In the same way that f of g of 10 gave us 10, and g of f of 21 gave us 21, we just have shown that f of g of x gives us x, and g of f of x gives us x as well. We have shown now, without any doubt, that these two are certainly inverses. In other words, f of x and g of x undo one another, right? Whatever you plug in for g of x, if you take that result and plug it into f of x, you're going to get your original input back, right? So this leads us to our test for if two functions are inverses of one another. And the rule is if f of g of x and g of f of x are inverses of one another, right? They must follow this composition rule, that f of g of x equals x and g of f of x equals x as well. In other words, no matter what the input is originally, the output will be x. And we test it with the general variable x, right? This way we know that for any input, we will get the same as the output at the end. Now, this is super, super duper important, okay? You need to make sure that this works, right? First of all, for both of these, and for all the values in the x in the domain of both f of g of x, okay? A couple important things here. If f of g of x or g of f of x, if either one of these don't equal x, then they are not inverses. Okay? So you can stop. If you find that one of them doesn't work, just stop. You're done, right? You've concluded that they're not inverses, okay? Also remember, right, the domain and range also switch. And this is not a way to really prove that they're inverses, but it's a good sort of reminder or another sort of check on the fact that two things may or may not be inverses. For example, in both of these functions, in f of x and g of x, the domain and range are negative infinity to infinity because they are lines, right? Okay, and just because they switch doesn't guarantee that they're inverses, but it is something that we can also kind of use to analyze or explain why or why not something might be an inverse. So just another tool to use, okay? So I'm going to do A, B, and C with you. And we're going to use the composition test to show that the functions are inverses or show that they are not inverses, okay? First thing I do here is I take a look at f of x and g of x, and I think to myself, you know what? There's no domain restrictions going on, nothing that can make either one of these functions undefined. There's a 2 and a 4. So let's go ahead and try our f of x and g of x, okay? Let's do our f of g of x, and we'll do our g of f of x, right? All right, so we've got f of 2x minus 3 over 4, right? That's our g of x function we're going to be plugging into f of x, right? So it looks kind of crazy at first because we're doing 4 times 2x minus 3 over 4 plus 3 over 2. Looks crazy because there's a fraction inside a fraction, but hopefully we realize, oh, those 4s and 4s go away, right? And we can start to see this expression sort of unravel here, right? 2x minus 3 plus 3 is 2x over 2. That equals x. Okay, so far we're in good shape, right? All right, I'm going to pick a different color just to differentiate between the two. Let's try g of f of x, okay? And we'll see what happens here. All right. So now we're going to take g and put f of x in. So 4x plus 3 over 2. Same idea. We're going to take 2 parentheses 4x plus 3 over 2 minus 3 over 4 equals 4x plus 3 minus 3 over 4. Because those 2's canceled, right? And that was a really helpful thing because now it's just down to, what, 4x over 4 equals x. So we can conclude here, right, f of x and g of x are inverses. We did our composition test. Nothing bad happened. We got x both times, right? And we can sort of make sense of the fact that they're inverses by looking at their operations, but we'll get to that in a bit. This is a great example. You might be thinking to yourself, these sure look like inverses, right? The square root of x and x squared are inverse operations. However, right, we've got to be super careful about how we go about the compositions, right? So let's start with f of g of x, okay? So I put g of x inside, right? I have x squared. Now, I want to think to myself, I'm taking the square root of x squared, right? It's very tempting to say, okay, the square root and the square just go away and you get x. But I want you to think about, what if we put in f of g of negative 3 for a second, right? Let's just take a number. If you did g of negative 3, you would get 9, right? Do we all agree negative 3 squared is 9, right? If you then apply f of 9, you get 3, right? Notice what happened here. When you plugged in negative 3, you got 3 out. In other words, this is not the same as this. When you plug in a negative number, because you're squaring it and then taking the square root, it's always going to come out to be a positive, right? If you did the same with g of negative 5, you'd get f of 25, and then you take the square root, it's going to be 5. So in other words, all of the negatives become positives, and we know how to deal with that, right? All of the negatives becoming positives means that this is actually the absolute value of x. Okay? So no matter what x is, right? If x is a positive number, we are going to get the same out. But if x is a negative number, we are not going to get the same out. So this is not x. It's the absolute value of x. So automatically, right, we can say f of x and g of x are not inverse functions. Okay? You may be thinking still, Mr. Gat, these are inverse operations. True, but those functions, the way they are written, are not inverse functions, right? When we take the square root of x squared, we get the absolute value of x, right? We cannot say that these are inverses, okay? Let's do one more. You may be looking at this one and thinking to yourself, well, this looks like the same exact example, right? Let's take a look. If you did f of g of x, okay, and you got x cubed, right? And then you applied that here and you did x cubed and cubed. Well, let's see. Do we get x, or the absolute value of x, out of this? Well, it looks very similar to this last one. So you might be thinking, well, you said that should be the absolute value. Let's try a number again. Let's try negative 3 again. All right. The question is that going to become positive or is it going to stay negative? Well, if you cube negative 3 times negative 3 times negative 3 is actually negative 27. If you take the cube root of negative 27, all right, you're asking yourself, what do you multiply by itself 3 times to get negative 27? the answer is still negative 27. So a negative, equals negative 3. Because, right, negative 3 cubed is negative 27. So in other words, putting negative 3 in the beginning resulted in negative 3 at the end. And that's true for any x, right? Putting a positive in at the beginning makes a positive. Putting a negative at the beginning makes that same negative. So you actually do get x out every time, right? A negative going in will come out as a negative. Okay? So far we are okay. Okay? If I do the same thing, right, with the other side, and I say to myself, okay, cube root of something, and I cube it, well, that should undo each other, right? The cube and the cube root. That will also give you x, right? Again, if you want to try a number, just to convince yourself, try the cube root of negative 64, right? That answer would be negative 4, right? And when you cube that, you're still going to get a negative because multiplying 3 negatives is going to give you negative 64, right? So it stays negative. So even though the last one, part B, with dealing with an exponent of 2 and an index of 2, this one we can say f of x and g of x are inverses. Okay. All right, so your task now is to try the rest of these, okay? Do your best, and then we'll jump to